This is session 14 for models in epidemiology and biostatistics. I'm Gordon Hilton Fick. So for sessions 13, 14, and 15, we're going to be looking at aspects of linear regression and a little bit about methods for analyzing measured characteristics not based on the mean. So linear regression based on hypotheses concerning the mean of a presumably symmetric distribution. Well, I thought I'd begin with some discussion about the use of linear regression and the crucial assumptions that are in play. It turns out that even back in the 1920s, when Professor Fisher and others were establishing the distributions in play for statistical inference with linear regression, many authors were noting that we have to be cautious about the use of these methods because they may well be very tied to the assumptions. Very early, there were authors who exclaimed the distributions are assumed to be normal distributions. And that assumption was thought even back then, essentially 100 years ago, that that could be an issue of some considerable concern. Well, so what are the assumptions for the application of linear regression? Well, there they are. I've listed them as 1, 2, 3, and 4. And again, some of you may well have seen some of this before and would have memorized these are the assumptions and what do we do? Well, it's never straightforward. So the first one being that the mean of the response of the outcome assumed to be measured here is a linear combination of explanatory variables. That's sum of k plus 1 terms. I'll be coming back to this. The second one, that the variance is constant. This is a standard assumption for the application of linear regression. Again, I'll be coming back to this. There are ways of handling the issues when the variances are not constant. Number 3, that the measurements we've recorded are statistically independent. This is a powerful statement. It's saying the joint distribution of these n measurements is the product of the marginal distributions and a whole range of other issues. Okay, statistically independent, a big deal. And in fact, for many of the sessions we're going to be dealing with later on in this series, Models in Epidemiology and Biostatistics, we're going to be dealing with circumstances in which we cannot make that assumption. And that leads us to a wide range of methods specific to issues when independence is clearly discredited. And as I mentioned, number 4 here, that these probability distributions for the outcome, for this measured characteristic y, are normal. Now, here we say, well, 2 things. If in fact we are prepared to assume that these distributions are normal, exactly, then the statistical inferences based on the t distribution and the f distribution are exact, insofar as the p-values and confidence limits have exact sampling properties. Now, what is much more likely the case in practice is that the conditional distributions are not precisely normally distributed, but we still anticipate And indeed, one could say we should be requiring that these distributions are at least approximately symmetrical, so that the study of these means, that's number one, even has any merit. Maybe there's other characteristics we should be studying if, in fact, the distributions are not symmetrical. All right. Now, if, in fact, it turns out that assumptions 2, 3, and 4 are reasonable, but assumption number 1 is not, this leads us to another large area in epidemiology and biostatistics, and that is the use of so-called non-linear models. Now, I want to take a few minutes to make some specific remarks about what we mean by non-linear models here. And in fact, in a later session in this series, we will be devoting all of our attention to models that are non-linear. But for now, just a little bit of a taste. We mean that there is no way to express the conditional mean as a linear combination of explanatory variables. Now, here's where it can get a little bit confusing, especially when you're orienting yourself to this. What we've seen already is that a model like the expectation of y is equal to beta naught plus beta 1x plus beta 1x squared is still called a linear model, insofar as the right-hand side of that equation is a linear combination of explanatory variables, x, 1, x, and x squared. So that you might think, wait a minute, that's a nonlinear equation, and it is. However, the model presentation in terms of this linear combination issue is different. All right. Now, just to give you a little bit of an example, there are some models that are not linear models. And for example, a very simple one, the exponential that I'm giving you there. There is no way of rewriting that in some way so that it is, in fact, a linear model. Similarly with the second one there, the logistic equation. Now, there are approximation methods and other transformation methods that can be used in specialized situations. That's not what we're going to be discussing here. In fact, what we're supposing is, not only with these two examples, the exponential and logistic, is the right-hand side a combination of characteristics that are not linear, but that we have, in fact, that the distributions have still the assumption of constant variance, are statistically independent, and that the distributions that add to the expectation are the normal distributions. Those are non-linear models with the other characteristics the same as we've seen elsewhere. Okay. Now, there are settings in which we can take a presentation of a model that doesn't look like it is a linear model, but in fact it is, that there is a way to write it that way. And just as one example of this, we've already seen the model for estimating relative potency. And we saw an equation that looked like this, where we have beta naught plus beta 1x plus beta 1k minus 1 times d times x. Well, you might think, wait a minute, that's not an expression that looks like that kind of expression we are requiring for it to be a linear model. But indeed here, if we simply replace beta 1 times k minus 1 with a new variable beta 2, then we do get a linear model. Okay. Now, there's another issue connected with assumption 1 that needs to be mentioned again. not only are we requiring that the mean be linear in the explanatory variables, but that we know in some sense that we've got the right set of those explanatory variables. Okay? So, for example, just very briefly here, if in fact we have that by some means we've identified that the conditional mean is in fact a quadratic in X, like this one here, but if we had only used the linear model, we would say that we have not satisfied assumption 1 because we've not used the correct, whatever that means, in a much more practical way. So do keep in mind that when we are using these expressions, when we're saying that the expectation is a linear combination of explanatory variables, we mean that we've found the right set. And indeed, there are methods that we will be looking at for addressing whether or not this assumption with the correct set of explanatory variables in some meaningful way has been used. All right, let's briefly take a look at the other assumptions. Assumption number 2, that we have constant variance. The variance does not depend on any characteristics. It is assumed to be the same for each participant in the study, for each of the measurements. Well, it turns out that there are certain settings in which we can use so-called weighted least squares, and where the weights are chosen to be proportional to the reciprocals of the variance, a fancy result attributed to Gauss and Markov. Now, in practice, one does not see this application of the Gauss-Markov method very often, at least not in my experience. However, in principle, it is one way in which the variances can be relaxed. The challenge is knowing what the weights should be can often be highly problematic. All right. And as I mentioned, assumption 3 is one where we have a huge collection of methods that help us to deal with circumstances in which statistical independence is not appropriate, or the lack of independence is in play. And there are many methods. We'll be looking at matching a little bit later, in a later session. There are issues of so-called blocking and clustering. There's a whole issue of methods appropriate to longitudinal studies. All of these are instances in which the independence assumption cannot be overlooked. And on the face of it, you may be thinking, this independence matter, is that a really big deal? Well, it sure is. It turns out that and we'll be looking at this in a much later session, that one can go seriously wrong by ignoring the fact that the observations have properties of dependency that are in play. So there's a lot here, and this is intended only to be an introduction. All right. So the fourth assumption, well, again, a big issue for you, the healthcare researcher, the epidemiologist, biostatistician, healthcare researcher, that if in fact we have that normality is not reasonable, then we have a whole complicated set of issues. Now, just wanted to mention one matter for you here before we go too far along. It does turn out that even if the distributions are skewed, if you have a so-called large sample size, then there are ways to show that the statistical inferences are still valid insofar as the p-values and their properties and the confidence limits in their properties will still have those sampling properties. However, we are then addressing issues, p-values and confidence intervals, about a characteristic that may be of little scientific value. If in fact the distributions are not symmetrical, then the study of the mean may be of little interest to the practitioner, to the researcher. Now, there is a large literature associated with methods to assess measured explanatory variables. Measured outcomes when the normality assumption is not appropriate. And again, we'll be coming back to some of these as we move further. Okay. But there is a whole fabric of issues related to so-called outliers. Or even more potentially troubling is the challenge of a circumstance in which the investigator is troubled that one or more of the observations may not follow the model that is being proposed. In other words, we might well have that of our n measurements that we have recorded for, say, n participants, that all but a small number are fine, but that there are those who, for whatever reason, may not be appropriate for inclusion in this analysis. In other words, they may well be individuals for which the model simply don't apply. They are essentially different. Now, we have methods for identifying those who are outlying, but we don't necessarily know we have found all those that plain simply don't fit. Now, this is a much more complicated topic. Again, I'm hammering on several, what you might say are foundational issues that dog almost any analysis, okay? Because if there are issues, for example, with the way in which the data has been collected, individuals' information has not been recorded properly, data entry issues, okay? Or data integrity issues of more complicated nature, where for some reason flaws impact on the whole data collection process. Right. So what do we got? We've got errors in our data. We've got blunders. We've got failures. It is unrealistic to expect that statistical methods are going to be able to fix this. Okay. It is vastly more important that, I mean, this sounds obvious. I guess it is obvious. But it is vastly more important to use due diligence as best you can at the design stage, at the data collection stage, so that these errors, blunders, and other failures are minimized. Okay. My mentor, one of my mentors, Professor Daniel Delury, one of his best quotations is, "The occurrence of observations we do not like is the commonest feature of all experimental and other statistical inquiries." Yeah. And then we need to be clear here. We can't remove observations just because we don't like them. Okay. Professor Delury. So you may well use an outlier methodology for detecting observations that don't seem to fit properly. And then you may be faced with the dilemma. do I remove them from my analysis? Well, Professor Delury said, the decision to reject observations should never be reached lightly. The decision to reject is a decision that the error system is out of control and we lose the essential basis for reaching assured conclusions. And then I love this part. In a way, the concern is less about the observations we remove than the ones we retain. How trustworthy are they if the error system is not to be trusted? Well, there you go, folks. What do we do with outliers? Well, I wish I could say I have a simple answer for you. There are methods of handling data sets for which outliers are notoriously present, so-called robust methods. Whole big literature there. Well, again, it is really more about the trouble. And how do you resolve it? Well, most researchers would say that if you have had to make some tough decisions and have done some data editing, data where you haven't been able to go back to the original records and see what the problem was, you've simply removed individuals, well, because you don't like them. And how do we proceed then? Well, it's never an easy matter, never a straightforward matter. Anyone who says, oh yeah, you can just use methods that are resistant to all of these dilemmas. Well, the answer is it could be, might be. How do we handle it? Well, tough issues. All right. So I wanted to now go to the topic of the assessment of assumptions. And there are several issues that are in play here. It could be that the assumptions I've numbered 1, 2, 3, and 4 up above are ones that are generally assumed to be the case in the study that for which you are conducting. That others have made the decision and that the assumptions hold. And it could be that the literature is strong enough that those assumptions ought to be taken into consideration. Okay, so that would be the first, maybe most ideal circumstance. The assumptions are used elsewhere in your literature, have been very carefully and thoroughly studied, and so all is it's fair then to assume that all is going to be well. On the other hand, it may well be that we need some means of using the data at hand to assess the assumptions. Well, it turns out, yep, there are statistical tests that can be used to assess the assumptions. I would say that in current days, the soundest methods for assumption assessment are the ones that are much more graphical in nature. On the other hand, people then say, well, so I'm supposed to look at a graphical assessment and somehow know what to do after viewing that graph. Well, the whole area of so-called pattern recognition and the graphical assessment of assumptions is again, it's a large topic, large literature. However, there are certainly instances in which the visuals will give you a very clear message, and other instances in which it will not. Okay, so graphical assessment skill is not easily learned. I would say that in my experience, when people are first learning about these methods, there's a temptation to see too much, to rush to rather hasty decisions that looks, maybe a look at the data makes one concerned, and there are much more crucial, maybe more important issues that are being missed. So again, it's always best to have your literature review done first, where you've determined from that lit review what it is that, what set of assumptions are generally accepted, and are you comfortable with those accepted assumptions applying in your work. There are also, that comes from the literature in many fields, in many subgenres of health research, circumstances in which we know that the assumptions don't hold and that one needs to do something. Maybe the one that I'll give as an example is one where it is widely known that some distributions are skewed in ways that are quite serious. For example, duration data can be one of the most notorious. The duration in, say, in days of an illness, the length of stay in hospital. Distance data can be also in situations where the distributions are not symmetrical. Another one is where the variables are already ratios. One of the more classic examples is the use of body mass index, or BMI. It is often well known from the literature that the body mass index as an outcome variable is not going to be symmetrical, and something's going to need to be done. The most common methodology here is the logarithm. It is also known from the literature that sometimes taking the logarithm may remove the skewness issue. For example, it sometimes turns out that analyzing as an outcome measure the logarithm of the BMI might well be a wise thing to do. The other one that's very well known is concentration of some say acid, and using the logarithm can give us the logarithm of concentration can sometimes give us a characteristic that is vastly more relevant to us. And that is, it could be one for which the logarithm of some characteristic has a name, and pH is the most widely seen. Okay, so I did want to mention here, and I hope I haven't confused this too much here in my discussions, but we're discussing the symmetry of the outcome variable, of the response variable, the health outcome, the variable that we are trying to understand in terms of explanatory variables. Now, I'll be talking more about this in future sessions as well, but the skewness of an explanatory variable is not per se a concern. In fact, the distribution of explanatory variables generally is not an issue. Rather, we are more interested in issues like linearity and additivity and the appropriateness of such. Now, another point is that sometimes a transformation is considered for an outcome, and then it may be that it's perfectly reasonable that some of the explanatory variables should be transformed in the same way. An example is a study, say, of household water consumption, a sort of study from environmental epidemiology. And we may be interested in such a study, say, with current time. Here 2005, a little dated. and we wish to understand the distribution of water consumption in 2005 in terms of some explanatory variables, but one of them, quite reasonably, might have been water consumption in the year 2000 or 5 years earlier. So it is almost always the case that if one is considering, say, for example, a logarithmic transformation of consumption here, in the outcome variable, that one would also transform the explanatory variable. Again, that means that the interpretation of the outcome in terms of the explanation will be enhanced if in fact both are transformed. This is an important issue. All right. So one of the ways in which you will see authors attempt to study the distributions is by a direct display of the graphs of the distributions. Now, if you can do so for each of the combinations of the explanatory variables, say there's just a small set of them, then that would be sensible. You could, for example, as we did earlier in session number 13, in session 13, I showed you the box plots for the 12 different groups. Now, if in fact we're confident that we have determined all the possible values of the explanatory variables, then displaying the distribution of for each of the groups is a sensible thing to do. However, you will see authors who will attempt to graph the distribution of the outcome ignoring the conditions. Unfortunately, this graph may tell us almost nothing about the individual conditional distributions, okay? This combination of all 12 of, say, for example, in the case of the earlier example we did, of just combining all of the data together into a single display may well be distorted by the possibly different conditional means. You may well be seeing, say, a bimodal distribution, for example, with all the data combined, and all that's saying to you is that, well, there's different means. Okay? So it is true that, and it can backfire on you in other ways. It can be that if you combine a set of skewed distributions inappropriately, they can sometimes look symmetrical when they're not. So it can really get you into trouble. All right. Another way to display characteristics associated with the distributions is to somehow remove the conditional means. In other words, to construct residuals. And this may be very provisional, right? We maybe use, for example, linear regression, but our goal here is more about assessing the assumptions rather than some sort of definitive analysis. So our goal isn't so much the inferences concerning the explanatory variables and the regression coefficients, but rather our focus is with the residuals. And are the residuals giving us an indication of trouble? For example, the residuals might give us an indication of skewness. The challenge is that if the distributions, if the assumptions are not holding well, then the entire analysis may be suspect. So the residuals may be misleading us. There's no simple, it's worth a try. And in fact, many authors will suggest this is what you should do. Very provisionally construct the residuals, and from a model that could be discredited, but then go ahead and then try a graphical method. Here, a simple box plot of the residuals can help, say, with the detection of outliers, which I've mentioned earlier, or Possibly enable a display that's often called the QQ plot. There's lots of names used here, or sometimes it's called a probability plot, where one is attempting to determine whether or not there's evidence of skewness, or evidence against symmetry, or evidence against normality. And for example, if we were to take our regression analysis we did in session 13, and here it is repeated, and then we save the fitted values, which I'll call BPH here for a blood pressure hat, okay, the estimates of the fitted values. I can then construct, using this predict option again with the option residuals, save the residuals here. These are the raw residuals in this instance. And if I use the instata, the command Q norm, I get a graph of the residuals versus the expected normal residuals. If in fact the normal distribution is appropriate for the errors, then we would expect that plotting the observed versus expected here. So here we have the observed residuals, and here are the expected residuals if in fact things are normally distributed. Well, here we'd be looking for trouble. Here we see an indication of this display of observed versus expected, and they're quite close to what we would have expect if in fact the errors are normally distributed. So here, and this is somewhat typical of blood pressure. Blood pressure measurements do appear to be symmetrical and indeed often at least approximately normally distributed. So we can see here that the blood pressure measurements show no sign of skewness. Now, notice here it is the blood pressure residuals. So here we've removed the signal first, very provisionally maybe, and then saw no indication of skewness. If in fact there was skewness, we would see that these values would tail up here. This would be giving us right skewed data, okay? Or possibly left skewed data where these numbers tail off down here. Okay? There's quite, if in fact you're considering trying out the assessment of the residuals using a probability plot or a QQ plot, you'll want to explore this in more detail. The next so-called probability plot is where one plots the residuals versus the fitted values. Okay? Such a residual plot here is, again, if in fact the residuals are in some sense dependent on the explanatory variable, then we would expect to see a relationship between these residuals and these fitted values. This display shows us nothing. If, on the other hand, we were to see some sort of nonlinearity pattern here, that would be an indication of the fact that there's some pattern here. If, for example, we're seeing that maybe some sort of curve here. A more common circumstance is where the residuals are, say, more tightly clustered for low values of the explanatory of the fitted values, and more widely separated for the high values of the fitted values. That sort of fanning out in a V shape is one that's sometimes seen. That's an indication where the variances are not constant and are in fact somehow dependent on the explanatory variables. And I'm just showing you here one in which all seems to be well. No apparent trouble. Okay. So there is no indication that the variability of residuals is somehow dependent on the conditions. Okay, it does turn out that blood pressure is one of those commonly taken measurements that is at least symmetrically distributed, as I've noted. All right, now let's now take a look at a second example. This is taken from the very fine book by Lawrence C. Hamilton. The book is called Regression with Graphics, a second course in applied statistics. Many of the illustrations in Hamilton's book taken from environmental epidemiology. And I'm going to take one of his examples, and it is one in which the researchers were concerned about the use of salt on the roads and the impact it would have on the salination of the wells. Here they were looking at a circumstance in which we might be wondering about a dose response. In other words, here we're going to be looking at a measure of how salty the water is from wells, from certain wells, and attempting to determine the relationship between the saltiness, the salination, and the distance from the nearest road, where salt was added to the roads, right? So here we're looking at a dose response issue. The closer we are to the road, we would anticipate the higher the level of saltiness or of chlorine in the water. Okay. And so we have then a response variable, that is the chlorine, and the distance from the road. I guess this was an American study, so it was done in miles. Now it turns out that Hamilton and the researchers that conducted this work determined that both the chlorine level and the distance from the road should be analyzed on a logarithmic scale. Again, this could be explored directly, and I've included the data as wells.dta so you could try this. If you look at the issue of the study of the relationship between chlorine and distance from the road, without the transformation, you'll see very quickly that there are issues. So this is an issue of data transformation, which I've mentioned only briefly so far. Further, we'll have a characteristic which we'll view as a potential confounder modifier, and that is the depth of the well. Maybe we might expect that the deeper wells would be somehow more protected from this dose response than the shallow wells would be. Or maybe we're just not sure. In this instance, then, if in fact the relationship between the log chlorine and the log road distance depends on the depth of the well, then we would say that the depth is a modifier. Okay? So the depth of the well is being viewed here as a potential modifier or potential confounder. Okay? So that means that we have in plan here then first taking the transformations as is done in Hamilton, and then constructing the regression analysis where we're going to have then the indicator for depth here, for deep here, right? Okay. So what do we got? We've got code, if one codes D equals 1 is deep here. So we've got W, and then we've got the distance from the road, R, on the logarithmic scale. Then we construct the product of W and R, that is the indicator for deep and the distance from the road on the logarithmic scale. Then we get this regression analysis, exactly as is done in Hamilton. And what do we see? Well, from this analysis, what we get right away is that the relationship between the log chlorine and log distance from the road depends on the depth of the well. There it is. The p-value is small. And you could then interpret these regression coefficients, and I strongly encourage you do so. What does that number mean? That is, in fact, a slope. It's a difference between two slopes. It is the slope for the deep well minus the slope estimate for the shallow well. Okay. And there is the slope estimate for the shallow well. In other words, when W is 0, then this coefficient, minus 1.1, is the estimate of the slope for the shallow wells. Okay? And then the sum of these two numbers is then the estimate of the slope for the deep wells. Okay? And what do we see? When we add the two together, we get a number that's nearly 0. Okay, so there's a little bit of the background here. In any case, it is instructive, it is helpful, I think, to go through the detective work before you look at the visual. And then when you look at the visual, you're going to see the message. Anyhow, here's the visual. There it is. Okay. Maybe the visual is even more interesting than the actual analytics given to us by the regression analyses here. So the green line is the shallow wells, and the orange line is the deep wells. And what do we see? Well, first of all, we can note that there weren't very many shallow wells. They're the blue dots here. Oh yeah, there weren't very many. However, even with that small number of shallow wells, we saw a negative relationship, and that was statistically significant. You could go back to the regression coefficients again. So that's saying that the closer you are to the road, the higher the log chlorine. So this is the log of the distance from the road, and this is the log of the chlorine. So what we're getting is this green line, unfortunately based on a comparatively small number of shallow wells. The majority of the wells were deep, and there was very little association between the log chlorine value and the log of the distance from the road. And this is well described in Hamilton's book. And we could, just to give you another application here, we saw that we could take the sum of the two regression coefficients to get this line here, which is essentially horizontal, or we could reverse code and have this as shallow well, and then the product of the shallow well indicator and the log of the distance from the road. Then we get that this regression coefficient, which is not statistically significant, is for the deep wells. The difference between these two numbers is then the slope for the shallow wells. And this number of 0.14 is the slope estimate for the deep wells. Okay. So I'm following the epidemiologic principles that are so classic here. We first we first address the modification issue, and we see that indeed the depth of the well here is a very obvious modifier. Now, this is, another big issue in connection with many environmental epidemiology projects, but, well, we didn't have a huge number of shallow wells. Why was that? Well, that might just be the reality. Tough topic here, perhaps. So, all right. Now, what I'd like to now do is take just a few minutes with methods of analyzing characteristics of our distributions when we're not prepared to use the mean. In other words, linear regression, just to be clear here, is about the study of the mean and how the mean is a function of the explanatory variables. However, it can be that, and this is seen now much more widely in health research, that one might wish to study, for example, the median, or perhaps the 25th percentile or the 75th percentile. In fact, the literature is really expanded a lot in recent years, where these so-called Q or quantile regressions are often tried. And indeed, the principles that we're using here are exactly the same. We're going to then have that the explanatory variables are a linear combination, like before. We'll assume the normality in principle here, the statistical independence here. Okay, but now we are studying the not the expected value, but we're studying the different quantiles. And if in fact we study the 50% quantile, then that's the median. And in Stata, a quantile regression where the quantile is the 50% is then so-called median regression. Okay. And what I have done here, just for illustration here, is shown you the same analysis here, but now using the fact that we are now studying the mean of these conditional distributions, okay? Sorry, the median of these conditional distributions. And in fact, you could try this with many different quantiles. It works very well. Now, what I'll just point out here very quickly for you here is our analysis of the median as the outcome measure does not dramatically change the results, and I'll let you explore this. Okay? We get essentially the same indication here, that the depth of the well is modifying the relationship between the median log concentration and the logarithm of the distance from the road. Now, just another point here is that although one might think that what we're doing is using distribution theory that is based, say, on the normal distribution again, in fact, it's slightly more relaxed. We are assuming that the conditional distributions have constant scale, possibly constant variance if the distributions have variance, and have the same shape. Okay, a big issue. This becomes, unfortunately, a somewhat big issue. So the distributions have to have the same shape, but can and must have constant scale, but are shifted only by the characteristics captured by the quantiles. So there's entire books on this, and this is an instance also in which the help files that one gets from Stata on QReg are quite helpful. And as I mentioned, there are many books on this topic And I'm noting a couple of them for you here. Suffice to say then that there's, in some health literature, I would have to single out actually in health sociology, where these methods based on quantiles are in considerable use, where the investigators are very concerned that they should not be studying the mean. So it does turn out that there are a wide range of methods for the assessment of the assumption of linearity. In a way, we've already seen one, and that is if we were to try either a parabola or a piecewise linear curve, we may get indications of whether or not linearity is okay or not. There are other methods of large literature concerning so-called generalized additive models, and that has not maybe caught on quite as much, and that's a complicated issue. Maybe much more in the attention of the literature now is people using the restricted cubic splines, which I have discussed earlier. And there's another whole range of methods based on something called fractional polynomials. Again, for future reading, especially if either restricted cubic splines or fractional polynomials are used in your literature, you'll want to explore this in more detail. So one more way in which we can assess an assumption is if we graph the residuals versus a measured explanatory variable. And here, we can graph the residuals versus the fitted values, and that's usually for detecting non-constant variance. However, if we graph the residuals versus a measured explanatory variable, like the log of the distance from the road, then we would also be interested in whether we see any curvature. And again, you may want to try this with, and I would invite you to do so, to take this data and repeat the analysis without the logarithmic transformation of the chlorine levels and without the logarithmic transformation of the distance from the road, and you'll get that's a nice little adventure. Highly recommended. However, on this particular scale, logarithm of the chlorine value versus logarithm of the distance from the road, we get nothing. We get no clear indication of curvature. Okay. And some authors will add a smoother to this display, perhaps to aid the eye in seeing issues that are worthy of further attention. And the smoother that is very often seen in this literature is the low-S smoother, LOWESS, one of the most widely seen in this field. So again, this becomes an area in which, if you're unsure about about interpreting the visuals, this is an area in which you may want to consider a consult with someone who has more experience with the interpretation of these displays. And that can be helpful too. Sometimes a very pointed set of questions for a consultant who's, say, a person with more experience in these things can be very, very advantageous for you. And I will also mention that in this literature, you will see some authors who still criticize the use of visual assessment because it doesn't have a p-value. Well, these are tough and challenging topics. What I can say is that if you feel as though you must add a goodness of fit test with a p-value, be aware of the fact that such goodness of fit tests are highly notorious, and that somehow the goodness of fit tests magically give you something that the visual assessment does not is usually just frankly untrue. Well, for this session, it is the first time I'm going to be providing you with an example from one of Sir Ronald Fisher's monographs, his book, Statistical Methods for Research Workers. And there are many authors who would say, and have continued to say for many years, that one benefits from reading Fisher, studying Fisher, and reading it over and over again. And I thought I would give you an example from Statistical Methods for Research Workers, page 136. This is not a health research topic. As many of you will probably know, Professor Fisher was affiliated, indeed was a member of Rothamsted Experimental Station for several years, which was largely concerned with agriculture issues. And this one is attempting to understand the yield of a particular grain in bushels. And this yield data was taken from 2 plots of wheat fields over a 30-year period. In one of the plots, called here 9A, there was a fertilizer treatment of something called nitrate of soda. And in plot 7B, there was a judged to be equivalent quantity of sulfate of ammonia. Okay, these issues are, the topic is grain yield, wheat yield, and the exposure here is the type of fertilizer. And further, in this instance, we will see that the year is viewed as a potential confounder modifier. And further, it turns out that Professor Fisher, at a very early stage in this analysis, determined that it was important to use what we now in health research would call the change score, or we would use a difference between, say, 9A, the 9A yield and the 7B yield for a given year. Now, this brings up a number of topics, and he gives a rationale for taking the difference, one that has been studied for years and years in understanding, essentially, data that is longitudinal. Now, for our purposes here, we will use the difference, because the issue was, and the nature of the question was, that not the 9A yields appeared to be gaining on the 7B yields. And was this gain significant? Okay, so here we're wondering about the nature of the relationship between the yield from year to year and the yield within year. So here we have 2 yields of a particular year, and Professor Fisher notes that there's a great deal of variation in yield from year to year, but similar in the 2 plots. Now, this brings up a large issue that we'll be discussing in another session and in a health context. But it's providing us with the rationale for looking at change scores here. All right, so that's part of the mix. Inevitably then, we're going to suppose for our analysis here that the change is the primary outcome, the difference between the 9A yield and the 7B yield. All right, and whether or not that change is a function of the year. Okay. So inevitably then, we're going to get a measure of the difference between 9A and 7B as a function of the year in which these yields were collected. Okay, so these years were, believe it or not, from 1855 to 1884. So we'll use a centering here, as Fisher did. We'll center on the average, which is 1869.5. Well. And then we will carry out a regression analysis of the difference on the centered year. Here we're wondering, is the difference changing with year? Because now the difference is going to tell us, is the difference between the two exposures here, the two fertilizers, changing over time? That was essentially the research question. And way back in the day, Professor Fisher carried out this regression analysis, this simple linear regression, which was a bit of a feat back in its early days before they didn't even have calculators, let alone computers. And we are quite nicely able to reproduce Professor Fisher's result here. We get this regression coefficient. This is now the estimate of the rate of change of the difference in yields, and that is per year. And what you can see is the difference is positive, and then has a p-value which is less than 5%, t statistic of 2.28. An indication that the change in yield is changing over time, is changing with regard to that slope. Okay. Now it's also, and here I'll just offer this as a sidebar, in statistical methods for research workers, in this section, Professor Fisher notes that it is likely that this relationship is nonlinear. He doesn't use exactly these phrases. He talks about that the relationship might be curved. Now, I don't believe that this particular analysis was carried out in any of Fisher's writings. I may have to stand corrected on that if in fact he did. But what we can do is carry out an analysis of whether or not the relationship is actually curved. And it's not hard for us. We can then take the square of the centered year in which the yields were measured and then carry out this linear regression of the difference in yields as a function of the year and the year squared. Now, what are we going to get, folks? We're going to get a parabola. And sure enough, Professor Fisher, back in that time, anticipated correctly. And there is evidence of nonlinearity and of a possible piece or an arc of a parabola in this particular instance. And you may find it instructive to save the residuals from both the linear and from the parabola and graph them. I would invite you to do so. Another technique that very closely resembles how we've analyzed the differences here is it could have been accomplished by an analysis of variance. Now this is, I'm kind of anticipating a topic that we'll be addressing in another session, but it is helpful to perceive how this could have been accomplished with the analysis of variance, using the actual yields, not the differences, and the year in which the yields were taken, and here the indicator for, here we'll say treatment, which is the indicator for the one of the two fertilizer treatments that was used. And then we have this cute way of getting the relationship between the year and the treatment. So the analysis of variance of this linear relationship could have been done by means of this analysis of variance. And in fact, it is now that this particular term here, capturing the linear relationship here, is the crucial one, okay? And in fact, we then are able to nicely reproduce the result from earlier, this p-value based on the difference of 0.03, and here we get the same 0.03. Further, we could have done the same thing with the analysis of variance and exploring the parabola, and that involves the actual yield, the year, the indicator for the fertilizer treatment, the linear and the quadratic, and again we get exactly the same. This p-value here of 0.0016 is the same as we got. It's been rounded a bit here, but it's exactly the same as 0.002 here. Okay. Now I'm going to stop there. There are methods that we will be exploring in a later session which make different assumptions and give us a regression analysis equivalent to this analysis of variance. But that's for another time.